Chapter Electrochemistry, the Part 4, the titration reaction or the direct reaction between oxidant and reductant. We previously explained that the electrochemical reaction can be realized by two different methods. The first is to do the reaction in two separate beakers, and this will form a galvanic cell that produces electricity. The second is to mix in the same beaker the oxidant and the reductant directly, so this reaction did not produce electricity, it will produce heat. So in this part, we will study the direct contact reaction. In the direct contact reaction, suppose Ox2 reacts directly with Rad1. According to this reaction, N prime Rad1 plus N Ox2 gives N prime Ox1 plus N Rad2. So during the reaction, the concentrations of Rad1 and Ox2 will decrease, those of Ox1 and Rad2 will increase. If we divide this global reaction into two half reactions, so we will obtain the transformation of Rad1 to Ox1. So Rad1 minus N electrons give Ox1, and this is an oxidation. So the couple 1 involved is Ox1 Rad1. Then Ox2 is transformed to Rad2. So Ox2 plus N prime electron gives Rad2. This is a reduction, and the couple 2 involved is Ox2 Rad2. And if this reaction proceeds in direction 1, so E of the reaction is positive, that means E reduction is always greater than E oxidation. And if we put these couples on increasing order of the potential electrode E, so Ox2 Rad2 has potential E greater than Ox1 Rad1. This electrochemical reaction will proceed till the equilibrium. So at equilibrium, E of the reaction is equal to 0. That means E reduction minus E oxidation equals 0. So E of the couples are equal. E couple 1 is equal to E of the couple 2. So is equal to a notation E of the solution. According to Nernst equation, E of couple 1 equal E0 Ox1 Rad1 plus 0.0592 divided by the number of electrons exchanged in the couple, so divided by N, log concentration of Ox1 divided by Rad1. And E of couple 2 equal E0 Ox2 Rad2 plus 0.0592 divided by the number of electrons exchanged in the couple 2, so divided by N prime, log concentration Ox2 divided by Rad2. At equilibrium, E of the couples are equal. So E1 equal E2. Therefore, E0 Ox1 Rad1 plus 0.0592 divided by N log Ox1 at equilibrium divided by Rad1 at equilibrium equal E02, E0 red 2 plus 0.0592 divided by n prime log concentration X2 at equilibrium divided by red 2 at equilibrium. So 0.0592 divided by n log X1 red 1 at equilibrium minus 0.0592 divided by n prime log X2 red 2 at equilibrium is equal E0 X2 red 2 minus E0 X1 red 1. We continue. We have to search for a common factors between these two relations. So if we multiply, for example, n by n prime, we have to put x1 and red 1 to the power n prime, because log x to the power n prime equal n prime log x, so we can cancel n prime and n prime. And in the second part of the expression, we multiply by the factor n, so we put x2 to the power n and red 2 to the power n. So this relation will take this form. Then we can take 0.0592 n and prime as a common factor. So 0.0592 divided by n and prime log x1 red 1 at equilibrium to the power n prime. We inverse x2 with red 2. So instead of the sign minus, we will have a sign plus. So plus 0.0592 n prime log red 2 divided by x2 to the power n, and all concentrations are at equilibrium, equal E0 x2 red 2 minus E0 x1 red 1. So 0.0592 divided by n prime is a common factor. We will obtain log expression plus log expression and log A plus log A plus log B. That means we have log A times B. So 0.0592 divided by n prime log x1 red 1 to the power n prime times red 2 x2 to the power n, and to note that all these concentrations are at equilibrium. So equal E2 minus E02 minus E01. So 0.0592 n prime log x1 n prime concentration times concentration red 2 at equilibrium to the power n divided by the concentration of red 1 at equilibrium to the power n prime divided by concentration x2 at equilibrium to the power n. So this expression is the equilibrium constant K. So 0.0592 divided n prime log K equal E02 minus E01. Therefore, K equal 10 to the power n prime. E02 minus E01 is E0 of the cell. So n prime E0 of the cell divided by 0.0592 at temperature 25 degree. Since when we use the Nernst equation log, that means the temperature is equal to 25 degree. In case n equal n prime, so we are not obliged to multiply by a common factor. So in this case, when n equal n prime, the relation is K equal 10 to the power n E0 of the cell divided by 0.0592, where n is N or N prime, since N and N prime are equal. And if we want to work at temperature different than 25 degrees, we have to use the expression Len, and we use RT divided by NF. So the expression of the equilibrium constant will be K equal E N N prime F Faraday E0 of the cell divided by RT. So what is the difference between the equilibrium constant of reaction indirect contact galvanic cell and reaction direct contact, which is the titration? In the galvanic cell, the equilibrium constant K equal 10 to the power N electron exchanged in the reaction times E0 of the cell divided by 0.0592. And in the case of the direct contact, the expression of K equal 10 to the power number of electron exchanged in couple 1 times number of electron exchanged in couple 2, E0 of the cell divided by 0.0592. Conditions of quantitativity of the electrochemical reaction. Consider the following electrochemical reaction between red 1 and Ox2. So K of this reaction can be given by two expressions. If the temperature is at 25 degrees, it's easier to use K equal 10 to the power number of electron exchanged in couple 1 times number of electron exchanged in couple 2 times E0 of the reaction divided by 0.0592. At temperature T, we can write K equal also EN prime F E0 of the cell divided by RT. Previously, in the previous parts, when we talked about the quantitativity of the reaction, we said if the value of K is very high, so this reaction is complete, or if the value of K is very low, this reaction is limited. We could not compare K of the electrochemical reaction to the factor 10 to the power 4, since most of the electrochemical reaction have stoichiometries different than 1, 1, 1, 1. For a reaction system between Ox2 and red 1, where N prime is equal to 1, so if E0 of the cell or E0 of the reaction is greater or equal 0.25 volt, that means K greater or equal 10 to the power 4, and the reaction in this case is quantitative. If E0 of the cell is less or equal minus 0.25, so K is less or equal 10 minus 4, we can suppose that this reaction did not proceed practically. And if E0 of the reaction is in the range minus 0.25 and 0.25 volt, so the reaction takes place, but this reaction is not quantitative. So now how to compare two reactions of different stoichiometries? K of these reactions could not be compared in this case. So we will suppose that the greater gamma is the reaction the more advanced. The Nernst equation and its relation to pH. For a couple oxide, the potential of the electrode is given by Nernst equation E oxide equal E0 oxide plus 0.0592 divided by the number of electron exchanged in the couple log concentration Ox divided by the concentration of red. If the couple oxide does not contain oxygen atom, that means H plus would not appear in the half equation, and in this case, the Nernst equation is independent of the concentration of H plus, so the Nernst equation is independent of the pH. Consider the following cell: platinum H2 at pressure 1 atmosphere, H plus at initial concentration C0 different than 1 molar, and on the right we have another couple in the cathode. We suppose that the couple at the cathode is not affected by H plus, so we don't have oxygen atom in this couple. E of the reaction equal E cathode minus E anode, and at the anode we have oxidation, so H2 is transformed to 2H plus 2 electrons. E0 of the couple H plus H2 is equal to 0, since this is the standard reference in electrochemistry, the standard electrode reference. The number of electrons exchanged is 2. The pressure of H2 is 1 atmosphere, and the concentration of H plus is C0 different than 1 molar. We apply Nernst equation on this couple, so EH plus H2 E oxrad equal E0 oxrad minus 0.0592 divided by N log rad divided by ox, or plus 0.0592 divided by N log ox divided by rad. E0 of H plus H2 is equal to 0, so the potential EH plus H2 equals 0 minus 0.0592 divided by 2 log the pressure of the hydrogen is 1 atmosphere divided by the concentration H plus square. So EH plus H2 equal, instead of minus, if we put the plus, we have to inverse the order of rad and ox. So EH plus H2 equal plus 0.0592 divided by 2 log H plus square divided by 1. So EH plus H2 is equal 0.0592 divided by 2 times 2 log H plus, and since the pH is equal minus log H plus in the solution, so EH plus H2 is equal minus 0.0592 pH. E of the reaction equal E cathode minus E anode. So E of the reaction equal E cathode. We suppose that E cathode is known, minus 0.0592 pH. So E of the reaction is equal E cathode plus 0.0592 pH. In this example, we observe that the concentration of H plus used will affect E of the reaction, or in other words, we have relation between E of the reaction and the pH. For the reaction to be spontaneous, so E of the reaction should be positive, therefore E cathode plus 0.0592 pH is positive, and the pH should be greater than minus E cathode divided by 0.0592. Relation between E and pH. Consider a couple oxrad where the potential of this couple is affected by the concentration of HCO+. So in other words, consider a couple ox-red containing oxygen. According to Nernst equation, E ox-rad equal E0 ox-rad plus 0.0592 divided by N log the ox and all components with divided by the rad. So E equal E0 plus 0.0592 divided by N log ox concentration to the power alpha times concentration of H2O plus to the power M divided by the concentration of the rad to the power beta. So E equal E0 plus 0.0592 divided by N log H plus to the power M plus 0.0592 divided by N log concentration X to the power alpha divided by rad to the power beta. So E equal E0 plus 0.0592 M log H2O plus divided by N plus 0.0592 divided by N log concentration of ox and rad according to the stoichiometry. So E equal E0 minus 0.0592 M over N pH, since the pH equal minus log H2O plus 0.0592 divided by N log concentrations of ox and rad according to the stoichiometry. So this relation is equal to E0 constant minus 0.0592 M over N pH for a determined concentration of H2O plus used in this couple, so the pH is constant. So E equal E prime 0, which is equal to E0 minus 0.0592 M over N pH, and therefore the expression is like Nernst equation, E equal E prime 0 plus 0.0592 divided by N log ox to the power alpha divided by the rad to the power beta. E prime 0 is the dependence of E on the pH, and E prime 0 is called the apparent standard potential where the pH equals 0. For pH equals 0, E prime 0 is equal to E0. So this relation shows the effect of the concentration of H2O plus on the potential of a couple. And as delta G0 equal minus NFE0 and delta G equal minus NFE, so the apparent standard Gibbs free energy delta G prime 0 equal minus NFE prime 0. So the apparent standard potential E prime 0 is variable for each value of the pH, so for each value of concentration of H2O plus used. The pH affects the equilibrium potential of a redox couple and is used also to define the predominant species. The variation of E prime 0 as a function of the pH will be a decreasing straight line, since the equation is identical to y equal ax plus b, and the slope of the line is equal minus 0.0592 m over n. If E prime 0 is equal to E0, so the couple is inert to pH. And E equal E prime 0 plus 0.0592 divided by N log concentration X to the power alpha divided rad to the power beta. That means if E is greater than E prime 0, so log X over rad will be positive, and in this case the oxidizing agent predominate. And if E is less than E prime 0, the reducing agent is the predominant.